I'm Jason Grant with World Wildlife Fund, and this presentation is about the forests and the forestry that stand behind mass timber and other wood products. I'm going to start at a high level and state the obvious. Forests are vital to life on Earth. They're home to more plants and animals than any other type of terrestrial biome. They purify the air we breathe and filter the water we drink. They mitigate flooding by acting as giant sponges, soaking up and gradually releasing rainwater. They build soil and prevent erosion, and they provide livelihoods for hundreds of millions of people around the world. Forests are also one of the keys to addressing the climate crisis, both because they store vast quantities of carbon already and because they have the potential to mitigate global warming by drawing down a significant portion of the excess carbon now in the atmosphere. Forests can be veritable engines of carbon removal. Trees absorb CO2 and use sunlight to convert it to sugar, which is carbon-based and combines with other ingredients to make wood and grow the tree. The chemical composition of wood is about half carbon that will remain safely socked away until the tree dies or is cut down and its wood rots or burns. Wood construction can therefore be seen as a way of absorbing excess carbon from the atmosphere and locking it away for the long term in buildings. It seems like common sense that substituting wood for concrete, steel, and other relatively energy-intensive materials used in building construction would be an effective way to reduce net carbon emissions. And there are many studies that back this up, although their calculations of the magnitude of the substitution benefit vary. What too often gets left out of considerations of the potential benefits of wood use, however, is the impact of logging on forest carbon. This term refers to all of the carbon stored in a forest, including what's above ground in live and dead trees and other vegetation, as well as what's below ground in roots, fungi, and soil. It's important to note that forest carbon stores are at their highest in primary forests. Also referred to colloquially as old growth, a primary forest is one that has remained relatively undisturbed by human activity. While there are many types of forests, generally speaking, the amount of carbon in living and dead biomass and soils is pretty much maxed out when the ecosystem has reached a climax state. Some argue that mature forests are quote-unquote decadent and stop absorbing carbon, so we should cut them down and plant new trees. It's a fact that as forests age, emissions from tree mortality gradually increase until eventually, when the forest reaches climax, emissions and sequestration more or less come into balance and carbon stores plateau. But when such a forest is logged, we lose a lot of that carbon in the atmosphere, and it will take a long time to reabsorb. So it makes no sense to replace old forests with young tree farms. Doing this creates a carbon debt that will only be recouped if the plantations are left alone for hundreds of years. Net-net, old forests store enormous amounts of carbon and are unique and precious ecologically, so it's vital to protect what's left of them. But there's also a huge climate benefit if more younger forests are protected and allowed to grow instead of being logged. If this happens, emissions of forest carbon will be reduced, and they will continue to sequester CO2 in ever larger amounts for a long time. Recently, scientists have begun referring to this strategy as pro-forestation and are elevating it as one of the safest, most effective, and low-cost approaches to carbon removal and climate change mitigation available. In the coming decades, when the window to avoid runaway climate change is closing, action is most urgent. Protecting more secondary forests will result in more avoided emissions and carbon removal than will logging them and turning them into wood products. Afforestation is even more important as a climate solution than planting new trees, also known as afforestation, because the latter won't make much of a difference in the next couple of decades when climate action is most crucial. This is because small trees just don't store all that much carbon. You may have heard that young trees grow faster than older ones, and this is true. But what really matters isn't the rate of carbon removal, but rather the quantity. A 5-year-old sapling grows fast, but it's so little that the amount of wood it adds every year is comparatively small. A 100-year-old tree grows slower than the sapling, but it's much bigger. So a lower growth rate translates into a larger amount of wood added and carbon stored. Old trees store the most carbon. One study found that in natural forests around the world of all types, only half of the carbon is stored in the largest 1% of trees. Not all forests can or should be protected. Society is going to continue using forest products, and as we know, the alternatives are often worse. But we should recognize that forest management impacts forest carbon stores at all scales, from individual trees to forest stands to entire landscapes, and results in near-term losses of forest carbon, even if reforestation occurs after timber harvest. When trees are cut, much of their stored carbon is released as roots rot and logging slash, such as branches, leaves, and needles, decomposes or burns. More is lost as the log is processed into wood products and the downfall rots or is burned for power. Only a portion of the carbon in a live tree is carried through to the end of the processing chain and stored for the longer term in wood products. When forest stands are logged, it causes a release of carbon stored in soils as well as vegetation. For those not familiar with the term, in the context of forestry, a stand is a limited and distinct area that is subjected to a specific set of management techniques. Logging across large landscapes can be a major source of net CO2 emissions, especially if more mature natural forests are converted to intensively managed tree farms. Logging accounts for 85% of emissions from U.S. forests, more than 5 times those from forest conversion, fire, wind, insects, and natural tree mortality combined. In Oregon, clear-cutting millions of acres since 2000 generated 16 to 32% of total emissions from all sectors, making logging one of the state's biggest carbon polluters in that period. Emissions of forest carbon from logging will be removed if forests grow back. But whether harvesting timber at the stand or landscape level results in a net loss or gain of forest carbon over time depends on many factors. One critical variable is the starting condition. What was there before the managed forest? This chart represents 2 different starting conditions. The dark line is an old-growth forest, and the light green line an open area where trees are planted. With the old growth, forest carbon starts high and drops steeply when it's logged, while with afforestation, it starts low and builds for several decades. The stand represented here is logged once every 40 years on a sustained yield basis where tree growth and timber removals are in balance. The level of forest carbon drops with each harvest and then builds back up before the pattern repeats. On average, once the management regime starts, it stays about the same, but where the starting condition was old growth, the net carbon loss is substantial, whereas with afforestation, it's the opposite. As the preceding slide shows, it's relatively straightforward to visualize how forest management impacts forest carbon stores at the level of an individual stand. However, the picture gets more complicated at the landscape level where numerous stands are being managed simultaneously. Let's visualize the managed forest landscape as a bucket and forest carbon as the water inside it. It's made up of multiple stands that have been logged at different times and are in different stages of regrowth. Some are taking up carbon and some are releasing it. The challenge is to determine how all of these offsetting inputs and outputs affect overall carbon stores. And we need to do that to understand the differing effects of different approaches to forest management. As I noted previously, carbon stores are highest in primary forests. The water in the bucket is at or near the top. This level is never static, however. The bucket has leaks. Trees are constantly dying and rotting, releasing carbon into the atmosphere. But even a leaky bucket can hold water as long as more water is being poured into it. At the same time that carbon is being emitted from the forest, it's constantly being absorbed from the atmosphere. Again, the amount of water in an old growth bucket will remain fairly constant over time. When the forest is logged, it impacts both the amount coming into the bucket and the amount leaking out, but the larger impact is on the leakiness. The more holes you have, and the bigger they are, the leakier the bucket. And the leakier the bucket, the less carbon it will store. In this analogy, the number of holes represents the frequency of logging, and the size of the holes is related to its intensity or severity. The large clear cuts characteristic of conventional industrial forestry can be pictured as bigger leaks, and the relatively frequent harvests can be pictured as more numerous ones. On the other hand, less intensive logging that occurs less frequently can be pictured as smaller, less numerous holes. As trees regrow after logging, more carbon gradually flows in, less escapes, and the level in the bucket gradually builds back up. But each time logging recurs, the bucket again gets leakier and the carbon level falls back down. And again, the more intensive and frequent the logging, the farther it will fall and the lower the average level will be. If there's a transition to climate-friendlier forestry, on the other hand, the holes get smaller and less frequent, and the bucket becomes less leaky. The average level will build up and remain higher so long as the management system is continued. Forest carbon stores are significantly increased. Again, only a portion of the carbon stored in harvested trees is carried over in wood products and can be stored for decades in buildings and other long-lived applications. This too represents a carbon store that can increase over time if the number of wood buildings also grows. And if there are reduced overall emissions as a result of substitution, this benefit will accumulate with time as well. However, any potential gains are offset when logging to produce the wood results in significant net decreases in levels of forest carbon. If, on the other hand, the wood used in building construction comes from improved forestry practices that build it up, then any substitution benefits will be enhanced. Thus, improving forest management and increasing forest recovery and protection are key to mitigating climate change. The steps we need to take in order of impact and therefore priority are as follows. First, logging of the world's remaining intact primary forest must cease. In North America, primary forests should be conserved where protections are not in place or are inadequate. Second, protections should be strategically extended to allow for proforestation of wide areas of previously logged forests, letting them grow back and recover their ecological and carbon storage potential. In some cases, this process of recovery can be aided through active restoration. Where logging continues, forest management should improve so as to increase average levels of carbon storage and maintain or rebuild ecological integrity. Some ways to do this are by managing less intensively, for example, selective logging or smaller, more widely distributed clear cuts, higher levels of retention, leaving more live trees behind after a timber harvest, and lengthening rotations, the time interval between cuts. Tree plantations have a place, but they shouldn't be established at the expense of natural forests. Because complex forest ecosystems store more carbon than plantations and are more resilient in the face of climate change, many existing plantations should be restored to a more natural condition. Finally, afforestation is desirable because it brings carbon benefits and will increase wood supply in the longer term. But, as has been noted, it takes decades for newly planted trees to achieve the levels of carbon removal and storage that can be realized much more quickly through proforestation and a large-scale transition to climate-friendlier forestry. Reforms such as these would not only improve the management of forest carbon, they'd yield numerous other important environmental benefits, including less damage or improvements to wildlife habitat, relatively higher ecological complexity and biological diversity, and reduced negative impacts or improvements to soil and water quality. As it happens, what is better for carbon is nearly always better for all of the other critical ecosystem values and services forests provide. Will increasing mass timber construction and wood use more generally be a climate solution? There's a simplistic narrative out there that goes more or less as follows. Trees suck carbon out of the air that gets stored each time we use the wood in buildings and elsewhere. We reduce emissions by substituting this wood for other materials. And this process will build if we expand wood production and consumption. The conclusion that follows is that the larger the area devoted to forest management, the better off we'll be. But hopefully by now, it's clear that whether or not using wood will help us solve the climate crisis depends entirely on where it comes from, where it does not come from, and how it's harvested. A significant increase in wood use that's satisfied by an increase in logging that contributes to forest degradation and deforestation will only deepen our problems. The key question is, will using more wood result in an overall decrease in atmospheric carbon and an increase in carbon stores? If we lose sight of forest protection, restoration, and stewardship, the answer is almost certainly not. Thanks for watching this presentation.